record to this. So, ladies and gentlemen, good morning from Greece, from Crete, from the Hellenic Mediterranean University. I'm Kostas, and together with my colleagues from HMU, Professor Kavoulakis, we would like to welcome you to one more Athena talk. The aim of the Athena talks that we planned the last 4 years, and we are very happy that already we have completed 122 invited talks, this last 4 years, every Friday at 10 o'clock CET, is to introduce distinguished scientists, collaborators, and potential partners of our research groups here in HMU, and more than this, to facilitate the networking of different scientists through this activity of the Hellenic Mediterranean University. So today I'm very happy that I'm going to welcome not only a distinguished speaker, but a great friend. This is how do I consider Yakov, a friend that he has a very distinguished also studies. So a few words about Professor Tisler. He heads the Molecular Photonics Laboratory at the Bar Ilan Institute of Nanotechnology and Advanced Materials in Israel. The lab is focused on understanding light-matter interactions in nanoscale materials and devices, combining ultra-fast and near-field spectroscopy with thin-film deposition of optoelectronic devices. Prior to joining Bar Ilan Chemistry Department, Yakov was a postdoctoral fellow at the Massachusetts Institute of Technology in this famous group of Bulovitz that nowadays they have built a whole city around nanotechnology center in Boston, in MIT, where he investigated microcavity organic lasers, strong light matter coupling, and the excitonic interactions in J aggregates of cannon dyes and semiconductor quantum dots. Yakov earned his master and PhD from MIT, so it's a great distinction also to have an MIT graduate in this Athena talks, and his bachelor from another very famous university, UPenn. And holds, I didn't know that, probably this is an opportunity to invite Yakov in another activities of us, 12 US patents. So his research involves coherent coupling in light matter coupled organic lasers and polaritones, ultra high resolution scanning, microscopy and spectroscopy, applications of ultra-fast nonlinear spectroscopy for energy sustainability, novel approaches to organic crystal growth, and organic light-emitting diodes. The today talks are going to be about something that I think Yakov has developed and is one of the pioneers on the field, Super-Spectral-Resolution Raman spectroscopy using angle tuning of a Fabry Perot Etalon. I think that he combines his laser physics, and knowledge with the organic electronics and organic semiconductors, this kind of multidiscipline title and research that Yakov is doing. So Yakov, I would like to thank you. I would like to welcome you to this Athena talk. It's a great honor for us, and the floor is yours for the next, let's say, 14 minutes. Thank you.
Thank you, Kostas, for the invitation and for the introduction. And thank you all for your attention. So, as Kostas said, today we're going to talk about Raman spectroscopy and super resolution Raman spectroscopy, and then applying it towards characterizing diamonds. So if there are any questions, please feel free to ask, or we can try to take them at the end. Let me just go slide by slide here. Hold on a second. 1 second. How do I make the slides? Okay, here we go. So first, let me give you an outline for today's talk. I'll tell you a little bit about our lab. Then we'll do a little bit of a long introduction to Raman spectroscopy for those who don't know what it is all about. And it'll give a perspective of how we view Raman as well. And then we'll talk about super resolution in general and super-spectral-resolution Raman spectroscopy, which is the heart of our work. We'll give credit where credit is due to previous works in the field, and then what we're trying to do, how it's a little bit different, some of our key findings, and what we're trying to do next. And then, of course, open it up for questions, and thank you all for your attention. So here we go. A little bit about the lab. We're the device spectroscopy laboratory. We used to be the molecular photonics laboratory, but we kind of changed a little bit, went a little bit away from organics and more towards nano in general, and now focusing more on the spectroscopy and not just photonics. And if you come to the lab, you're all invited, by the way. If you come to the lab, you'll see that the laboratory, it looks like this from top down. It's got 3 parts to it, which are all connected. The first is chemical synthesis and sample preparation. Sometimes we even do a little chemical synthesis. And then the right part of the laboratory is where we do thin film deposition of organic materials. We work in a glove box, make optical coatings in a thermal evaporator like this one. The glove box is in the back. And then really the heart of hearts for the laboratory is the spectroscopy part of the lab here, where we take the devices that we make with the molecules that are synthesized, and then we try to do hopefully interesting work there to study light-matter interactions, or even try to come up with new spectroscopic techniques, and that gets done here. And basically, really, as Costa said, we're focused on near-field spectroscopy, Raman and low-frequency Raman, and other kinds of light-matter interactions. And of course, the magic really is in the students and the postdocs who come to work here. And Costas can help you get over here through an Erasmus grant. You should talk to him about that. Anyways, so let's get into what is Raman spectroscopy. So Raman, this is a picture of Sir Raman. He was the first Indian scientist to win a Nobel Prize. And it's a great story how he came up with the idea, invented the idea of Raman spectroscopy. He was actually on the way back visiting Lord Rayleigh in England. And of course, Lord Rayleigh was able to explain why the sky is blue based on Rayleigh scattering. And Lord Rayleigh said this is also why the ocean looks green. And Raman, on the boat ride back to India, was thinking that maybe Lord Rayleigh wasn't exactly correct. And when he got back to India, he formulated some experiments, and he was able to discover Raman spectroscopy. So you have to understand, we use lasers. Almost everybody nowadays uses lasers to do Raman. Raman invented Raman spectroscopy, discovered in 1928. This was, more than 30 years before the laser was invented. So it was an amazing discovery at the time. Anyways, Raman is usually a form of vibrational spectroscopy. And in vibrational spectroscopy, there's really 2 ways to study the vibrational modes on molecules. One is called direct IR spectroscopy, and then Raman, and I'll talk about both briefly. The idea is like this: if you consider a molecule and its energy levels, you'll have electronic energy levels such as the ground state that's here, that's also referred to as the HOMO, the highest occupied molecular orbital. And you'll have the LUMO, the lowest unoccupied molecular orbital. These are the electronic energy level manifolds. And within each one of these manifolds, there's vibrational sublevels. So with vibrational spectroscopy, we actually probe these levels. And these levels can be characteristic of the molecules in a number of ways. First of all, they measure the overall elastic properties on the molecular level and the reduced mass of the molecule. But they also can tell us much, much more. How so? Because for any given molecule, whether it's as simple as a water molecule or a simple alcohol or something much more complicated, there are many vibrational modes. When you think about all the different ways that the atoms that link together to form the molecule can vibrate, there can be rocking modes, wagging modes, stretching modes, scissoring modes, and each one of these natural modes has a characteristic spring, quote unquote, molecular spring distribution and mass distribution, and therefore a characteristic natural frequency associated with it. So basically, the vibrational modes, if you will, form a chemical fingerprint for each kind of molecule. And so, for example, if you would consider a relatively simple molecule such as toluene, which has this phenyl ring and one methyl group attached to it, you'll see in the infrared many different peaks or transmission or resonant absorption peaks that are due to all of the different mechanical modes that are possible. So for example, just the CC bonds, the carbon-carbon bonds on the phenyl ring, the way they stretch forms these different peaks or resonant drops in transmission or absorption peaks for this toluene liquid molecule. And this is using regular IR spectroscopy. Now, we like IR spectroscopy, but IR spectroscopy is, in a way, it's beautiful and it's elegant, but it's also complicated because you have to use this thing called an interferometer. You have to split your light source. You have to put it through 2 mirrors and carefully control the spacing between the mirrors, and so on and so forth. And the question is there another way to get information about the vibrations of a material at the molecular level? And the answer is yes. And for that, we use Raman spectroscopy. So in Raman spectroscopy, what you do is something quite different than in IR. In Raman spectroscopy, we take a laser and we shine the laser on the material. So this is, if again, we're looking at toluene, we shine the laser on a sample of toluene. And what we do then is we look at the colors that come back. Now, most of the light that comes back is at the color we put in. That's called Rayleigh scattering. But there'll be some slight changes in the color. And from those slight changes in the color, we're able to infer what the molecular vibrational fingerprint is of the material. Let me explain this in more detail. So for example, let's say we have our sample here. That's this gray block. If we shine laser light on it, some of the light we know is going to get reflected. That's this beam path. Some of the light is going to get transmitted. Some of the light's going to get absorbed. And usually you think, okay, that's it, right? You have 100% of the light goes in, some fraction will get reflected, some will get transmitted. Whatever's not reflected or transmitted is getting absorbed, right? The answer is no. There's also scattering. There's some small fraction, usually about, 0.1% of the incident light gets scattered. Now, most of that scattered light is called Rayleigh scattering. Rayleigh scattering means the color you put in is the color that's scattered out. So for example, if we're looking at this molecule and the wavelength of excitation we put in is a laser at 532 nanometers right here, okay? Most of the scattered light, about 99.9% of the scattered light will be at the exact same color we put in. That's called Rayleigh scattered light. So there'll be a very big peak of scattering at 532 nanometers. But there'll also be a very small fraction of the scattered light that goes to other wavelengths. And you can see those peaks here at these different wavelengths here. And these are the Raman scattered peaks. Now, interestingly, hold on a second. Interestingly, when you look at Raman scattering, some of the scattering is to longer wavelength. That's called Stokes Raman scattering. And some of it goes to shorter wavelength. That's the anti-Stokes scattering wavelength. And I just put this little equation up here because usually when we talk about Raman, we don't talk about wavelength, we don't talk about energy, we talk about wave number. So how do you convert between wavelength and wave number? You take the wavelength, you convert it to centimeters, and take 1 divided by the wavelength, and that gives you the wave numbers. So the Raman is actually a shift in the wave numbers. You take the wavelength you put in, the wavelength that comes out, you convert both to wave numbers and look at the difference in the wave numbers, and that's the Raman shift. And so you could ask a question, where does the Raman shift come from? Where does this change of the wavelength come from? It almost seems like magic. So for that, we have to think a little bit about how light-matter interactions work in general. For whenever you have a light-matter interaction, that must mean that basically, usually, there has to be some dipole of charge, some wire, some electronic wire on the molecular level, right, there has to be charges vibrating. That's how radio waves get generated. And since light is just like radio waves, just a different frequency, that's what Maxwell discovered back in the late 1800s. So since light, just like any electromagnetic wave, has to have electrons that are vibrating, it must be that there's electrons vibrating. So how does that work with Raman? The answer is because in Raman, usually the material is not even absorbing. The answer is when you shine a laser onto the sample, you induce a dipole. So that's a very deep idea. The material by itself maybe doesn't even absorb the laser. For example, you could have a piece of plastic. Plastic is transparent to visible light. There's no real absorption. But when you shine an intense laser, you will induce a dipole, and that dipole that you induce can then interact with light itself and radiate light just like a regular dipole. So as you might expect, because you're inducing a dipole, the induced dipole is at the same frequency and wavelength that you put in. That's the Rayleigh scattering. And that's why about 99.9% of the scattered light is at the same wavelength you put in. About 0.1% of the scattered light comes back at different frequencies, and that's characteristic of the material, and that's the Raman spectrum. So if you have to look here on this scattering diagram, you put in one color with a certain energy difference, and you get Rayleigh scattering, but you also get scattering to lower energy, that's the Stokes-Raman peaks, and higher energy, that's the anti-Stokes-Raman peaks. And actually, the Stokes and the anti-Stokes are mirror images of each other. Why? Because they're due to the coupling between the molecule, the vibrations of the molecule, and the incident light. Let's see how that works. Okay, so again, Stokes is lower energy, anti-Stokes is higher energy, and the energy difference is the vibrational energy difference. And how does it work? So there's some beautiful math, and I don't know if we need to go through all of it right now, but we can just say in a very short manner, the incident light has a certain laser frequency. Let's call that omega L of the laser frequency. The material itself has its own characteristic vibration, and because there's a light-matter interaction, there's a coupling. So you take the vibrational mode of the material and you couple it with the laser oscillation, and whenever you have coupling, you're going to get sidebands. And that sidebands means you get a frequency that's lower by the laser frequency minus the vibration, and the laser frequency plus the vibration. Laser frequency minus vibration is lower energy, that's the Stokes-Raman peak, and the laser frequency plus the vibration is the anti-Stokes peak. And that's why the Stokes and the anti-Stokes peaks are separated from the laser line by exactly the same energy difference. When you think about it, you can say, wow, that's pretty cool. So that means if there's a Raman Stokes shift to lower energy at 800 wave numbers, there's also an anti-Stokes shift at minus 800 wave numbers. It's called minus because it's actually higher in energy. And as it turns out, you can see there's a ratio between the Stokes intensity and the anti-Stokes, and that's because the material is basically, the vibrations are basically in equilibrium, and therefore there's a Boltzmann factor that relates the intensity of the Stokes and the anti-Stokes. And people have used this ratio of Stokes to anti-Stokes to actually figure out the temperature of the material when it's excited. Let's move on. So just to conclude this story of Raman, you can compare the Raman peaks with the infrared peaks, and sure enough, there is a correspondence, but sometimes you have Raman peaks that are strong and like this one here, and the infrared peak is weak, or you have peaks that are infrared strong and Raman weak. And today, people don't look at it usually as Raman or infrared. It's kind of both. Sometimes you study material with Raman, sometimes you study with infrared, and in the end, you get a picture of the vibrational fingerprint of the molecule. Let me say one more thing about it. Remember, in infrared, you're shining infrared light. In Raman, you're not shining infrared light, you're shining visible light, and you're looking at the scattering, and from the change in the wavelength, you're figuring out the Raman peaks. A few more things about this. So Raman is a very photon-starved process. That means for every million photons that come in, only about one is Raman scattered. So you have to work pretty hard to collect those small fraction of photons. And you also have to work really hard to make sure your laser excitation doesn't saturate your spectroscopic equipment, because it's so many times 6 orders of magnitude more intense. So you need some very good filters to block out the laser from hitting the spectrometer. When everything works, it can be really amazing. But because it's photon starved, there's a lot of light coming through, you have to do many things to try and collect more signal. For example, you try to use a wavelength that's shorter, or you do some other kind of tricks, such as what it's called surface enhancement or tip enhancement or nonlinear Raman. Let me talk a little bit about these techniques briefly, and then we'll go into super resolution. So first of all, why do you actually want to study Raman? Raman is really powerful. Give me an example. If you look at carbon, carbon has many different forms. It could be graphitic carbon, it could be like this piece of coal, diamond carbon, or even graphene. and monolayers of graphene. And with Raman, you're able to see the differences of the exact same chemical based on its structural orientation. Here, for example, you see difference in the Raman spectrum based on whether you have a thick layer of graphene or even 5 layers, 5 monolayers or 10 monolayers. Okay, you can even say, for example, how on a layer of graphene or other materials, when you get to the edge of the nanoscale layer, you see a difference in the Raman spectrum because you get more disorder. So that shows up as a different peak, like this one here, the D band in the graphene. And Raman can even be used to detect single molecules. And this is powerful because for example, in biology or biological applications, a lot of times you care to identify a single molecule that maybe, heaven forbid, is cancer causing or something, and you want to see that, and you need to be able to detect it with a very small amount of material. You can do that with Raman. And the way you have to do that is using something called SIRS, surface enhanced Raman, where you take your molecules, you put it in between like nanoparticles of gold. That creates something called a gap mode. And then any molecule that's between these gold mirrors actually gets gold spheres actually gets very strong Raman. And you can use it even to help identify cancer. I'm going to just show you 2 of my favorite applications of Raman. One is something called tip-enhanced Raman. Instead of putting your analyte onto nanospheres to get the SIRS effect, you actually take the nanospheres and bring it close to the material. This was invented by Renato Zinobili at ETH more than 20 years ago at this point. You take an AFM tip, you put nanoparticles, you bring that tip down into contact with your sample, and here's what you get. The Raman of your sample by itself could be pretty low intensity, and when you bring this AFM tip, you get much stronger signal, and now the signal is coming from just a few molecules underneath the AFM tip. So you get really strong enhancement, really high localization, and that's how TERS works. And the other favorite technique we have is what's called low frequency Raman. And the reason we like this one is because here we look at Raman shifts that are really close to the laser line, only a few hundred wave numbers away. And that can really tell you something about the nanostructure of your materials. So I'll give you an example here. This is a crystal of aspartic acid, just basically depending on whether it's all aligned in a regular way or whether it's oriented like in basically a changing fashion. Okay, you see very different Raman peaks coming out. If it's what's called enantiomerically pure, it's all right-handed or left-handed, you see one set of peaks. And if you vary the chirality, you see very different Raman peaks. So you learn something about materials even on the nanoscale, and you can even use low-frequency Raman to tell you about the size of your nanoparticles. So Raman has a lot of applications. Let me just say, okay, the size depends on the radius of the particle. So to summarize this first part, and for those of you who are not familiar with Raman, or even if you are, when it comes to Raman, again, it's a scattering process, and based on the change in the wavelength and the change in the energy between what you put in and what you get out, you can learn about the vibrational signatures in the material and even the nanostructure. And you have to be very careful not to get the laser of excitation into the spectrometer. You need very careful blocking filters, and then hopefully you're able to see the spectrum and learn about your material. Now, as you can imagine, okay, you can use it to distinguish between all kinds of materials. Here's an example between ethanol and methanol. But the main point that we want to get to now is the resolution of the Raman spectrometer. Here's an example from Bruker instruments. Depending on the spectral resolution of your spectrometer, you're going to get something that looks very different. Okay, so for example, if your resolution is 4 wave numbers, then your Raman peak might look like this Gaussian bell curve spectrum. And if your resolution is 1.5 wave numbers, you might start to see these individual peaks. If you have even better resolution, 0.5 wave numbers, you'll start to see more of the chemical fingerprints. So you can imagine that, back to this example of ethanol versus methanol, if you didn't have a high enough resolution, both the methanol and ethanol would just look like one big globular Gaussian peak, and you wouldn't know what you were looking at. You need good spectral resolution for the technique to really unlock the power of the technique. And what I want to tell you is there are already ways to get better spectral resolution. one way is to just use a bigger spectrometer. Let me just mention something about one of my professors, Arto Namiko. He's at Brown University, but we had a collaboration when I was at MIT, and he always likes to say there's a 30-year cycle in research, which means if you want to know what's hot today, just look back 30 years ago. You may see that the same exact thing people were doing already before. And of course, that's a humbling thing because, you think, wow, I'm doing something new. Actually, it was probably done before. But it's also a very powerful idea because if you want to get an idea of what's going to be done maybe in a few years from now, just look back 20 years or so, and you may have a better idea of what's coming next. So you can always make your spectrometer bigger, and that you get better spectral resolution. This is an example of an instrument by TriVista, by Princeton Instruments, where they take 3 spectrometers back to back to back. You get great resolution, much better than one wave number, but you can imagine this thing weighs over 100 kilograms. It's very heavy, very expensive, not accessible to everybody. And that's not really, well, it's a great thing, right? Who can say anything bad about it? Heaven forbid. But we wanted to try something else to get the spectral resolution to be higher. So in a nutshell, what our project is about here is we want to do Raman spectroscopy. We want to take a regular Raman spectrometer, not one of these huge, humongous ones. We want to introduce another optical element called the Fabry Perot interferometer or optical cavity. And together, if we put them together in the right way, we want to, by angular scanning, by turning the Fabry Perot and taking multiple measurements, we want to obtain super-spectral-resolution spectroscopy in general, and for us, super-spectral-resolution Raman spectroscopy. Okay, so let me just say that the idea of super resolution or localization microscopy actually garnered the Nobel Prize in 2014 by these 3 winners in chemistry, Eric Betzig, Stefan Hell, and William Murner. And there they did a number of techniques to break the resolution limit in a microscope. So usually the resolution limit, called the Abbe limit, basically says due to the size of the wavelength of light, you can only resolve things that are so small and not more. And they came up with different ways. Each one's labs, right, and teams came up with different approaches for how to break that diffraction limit. And this is an example of a microscopic image using a regular fluorescent microscope or using super resolution techniques. You could see that you get much higher spatial resolution out of the microscope. So the idea of super resolution overall, and especially in microscopy, it's a great idea. It's very popular nowadays, already 10 years since the Nobel Prize. We're not doing that. We're doing something that has the same flavor, but a different approach. And I'm going to tell you about that now. The basic idea is also not new. It comes from the idea of moire patterns. So let's imagine you have a certain target, okay? And by target, I mean, a semiconductor target. It's basically lines that are very narrow, very closely spaced. Now your camera, maybe the spacing between these peaks is a few nanometers or 10 nanometers. Of course, with a regular camera with visible light, you're not going to be able to see such a thing. And for example, this might be what your camera resolves when you take a picture. It basically looks washed out. So you don't see the individual lines anymore. You see, again, something that's blurred. So the idea is, if you can take another pattern with similar spacing to the pattern of your target, and you overlay those two, then that combination you can image with your camera. Now the combination, because of the interference between your target and the additional pattern you put in, you'll see new peaks. But those peaks, again, don't have enough resolution. So what did you gain? You had a mess, and now you have another mess. Yeah, but now you have a controlled mess. Meaning, if you can control the phase between the pattern you put in and the target, then as you vary the orientation of your target, the target relative to the pattern you put in, you'll see new combinations. And from watching how the new combinations change, you can maybe learn or infer what the target has to be. Let me give you an example. It's called a moire pattern. This was a moire pattern done with graphene. So the graphene itself, the atoms are spaced super close to one another in this hexagonal packing. If you take another layer of graphene and put it on top, then if you look at the emission through, you'll see a periodicity that's a much longer wavelength, so to speak. Their periodicity will have a longer period because of this interference effect between the two. Okay, so the idea is like this. We have a certain spectrometer, and if we add a Fabry Perot, which by itself has very high spectral resolution, even if our spectrometer cannot resolve that, maybe together we can use a super resolution approach to infer a higher resolution from our actual material. Let me show you how it works. So again, as I said before, with the 30-year cycle in research, this concept of taking a spectrometer and adding a Fabry Perot interferometer is not new. It was actually developed by these two scientists, Persson and Gabel, who were in Pasadena, California, and they were working on astronomy. So they published a beautiful paper where they took an FTIR, no, not an FTIR, I made a mistake, a grating spectrometer for the infrared, okay, like an FTIR, but not. And they combined it with a Fabry Perot Etalon that they put before the spectrometer. And they said that using the two combined, they could see better resolution. Now, they didn't call it super resolution, and they certainly didn't use it for Raman, but you still see that there is the idea of taking a grating-based spectrometer, like we have in the Raman, and the Fabry Perot, and combining it together. Now, let's give credit where credit is due. In the world of Raman, really the first person I know of who invented, and I think he is the inventor, he has the patent on it, is Professor Zev Zalewski, also from Bar-Ilan University. Professor Zalewski is an expert in super resolution imaging on using this concept of the moire patterns to develop better imaging with cameras. And Zev said, let's try to take this to spectroscopy. So we helped him out with some of his first papers, not his very first paper, but some of his first papers. And again, the idea was, if you have, you take a laser, for example, or you take a Fabry Perot, and you combine that with your spectrometer, maybe the peaks you get will be quite broad in your spectrometer. But then if you can do this again and again, either by varying your laser wavelength or by slightly tuning your Fabry Perot interferometer, maybe you can extract some kind of super resolution peaks and get better a better Raman fingerprint from your material. Okay, so we decided to take up the challenge to see if we could improve on Zeb's first results and his lab's first results. And so we bought some Fabry Perot Etalons from a company in Canada called Light-Machinary. I put a link to them here because I want, if you're interested, you can go ahead and buy one yourself. This is a great company. They are very accessible. And with this, and basically what we bought is an Etalon. I'll explain to you more what it is in the next slides. And we tried to say, can we get super resolution? And we had an application in mind. And that application is to try to do crazy resolution Raman to see the difference between natural and lab-grown diamond. Because diamond has one Raman peak, and we figured let's work with something with one Raman peak because it'll be a lot easier than something with many Raman peaks. So we said, let's look at diamond, and maybe we'll see some differences between a real versus real. They're all real, but a naturally grown diamond taken from the ground, mined from the ground, or one that was grown in a laboratory. Anyways, let me tell you now what a Fabry Perot Etalon or interferometer is all about. So basically, you take two surfaces that have a reflective coating, and you control the spacing between the two. And if you shine light on them, you'll see this beautiful series of ring patterns. And the ring pattern depends on a number of parameters. First of all, it depends on it depends on the reflectivity of your mirrors. Okay, so if your mirrors are just a little bit reflective, 10%, you'll see that the transmitted light depends on the wavelength, but it's not a very strong function. But if your reflectivity is high, let's say 90%, then all of a sudden you'll see some wavelengths that go through and others are blocked. And this is due to optical interference. So certain wavelengths, if they satisfy the standing wave condition between the two mirrors, you'll get resonant transmission, as are these peaks, whereas other wavelengths will get reflected back and destructively interfere, and they'll get suppressed. So you have a measure of how good the Fabry Perot is at transmitting certain wavelengths, filtering them through, and rejecting the others out, and that's called the finesse. If the finesse is high, you do a very good job of filtering, and if the finesse is low, then you don't do such a good job of filtering. And you can actually, there's beautiful formulas. I gave you a few here, but basically the intensity of the Fabry Perot, it's a function of the reflection of the mirror coatings, and it's also a function of the spacing between the two mirrors and the wavelength and also the angle. So you can change the spacing between the mirrors and you'll see a different pattern of wavelengths go through, or you can change the angle or the wavelength. Let me show you a little bit more about that, putting it all together. So for example, if you take a laser like we did with 532 nanometers and you shine it through the Fabry Perot, just by varying the angle of the Fabry Perot, you're varying this angle here, theta, that varies the phase between the two mirrors, and that changes the amount of transmission or reflection you're going to get due to the amount of interference the light has with the structure. So you can see based on one angle, you have a certain amount of counts. If you change the angle, you get less counts. And if you change the angle again, you get even more counts, okay? So our idea is to take the regular spectrometer, combine it with the Fabry Perot Etalon. The Fabry Perot Etalon has much higher spectral resolution than our spectrometer by itself. So that's like the idea of the super resolution, but then we have to just vary some parameter within the Fabry Perot, in our case, the angle, and take a number of spectrum, put them all together, and then do some kind of algorithm to get back the super resolved Raman peak. We did that, and it resulted in a paper, and I'm going to now present, thank God we got a paper out of it, and we got a nice result, and I'm going to now explain this result in some more detail, step by step. Okay, so here's our experimental setup. We have a laser. We worked with a 532 nanometer laser. We take that laser, we excite a sample through an objective. It was a sample of diamond, and we have some Raman filters to block the laser. We have a spectrometer, and we put a Fabry Perot in the path in order to get this super resolved effect. And what we're doing is we're varying angle instead of varying the spacing between the mirrors, and we're seeing the Raman shift. Okay. In particular, the Raman shift for diamond, the Raman shifted wavelength is at about 571 nanometers. And when we took this Fabry Perot Etalon, we varied the angle in steps of about 0.02 degrees. So for every 1 degree, that's 50 spectra, and we did about 4 degrees of angular tuning. That means we need 200 spectra. Okay. So one big challenge that we kind of had to deal with is alignment of the Fabry Perot Etalon. Costas, how much time do I have?
You have 10 more minutes.
Okay, fine. Great. Okay, one big challenge is the Etalon position. For example, it's really important that this Etalon be exactly, that its axis of rotation be exactly in the center of the Etalon. Let's consider that. This is the ideal case when the Etalon is exactly in the middle of the axis of rotation, but you could have a situation where it's a little bit off. And if it's off, that means all of the mathematics that I showed you is not really going to work exactly. All the modeling is not going to work exactly. You're going to run into a problem. So what we had to do is come up with a method to align the Etalon. And that's a common theme when it comes to experiments is, the details are really, really important. So what we did is we said, voila, we don't know what we're doing, but let's start and let's shine the laser into the Etalon and detect the intensity of the laser that comes through as a function of turning the Etalon. Because we figured we know what it's supposed to look like when it's properly aligned. The peaks for the intensity are supposed to be symmetric around a certain angle. And initially they weren't. And that was indicative of saying that our alignment was not good. So we kept adjusting the position of the Etalon inside of its holder until finally we got nice symmetric peaks. And when they're nice and symmetric, sure enough, we're supposed to get a spectrum that looks like this. I'm not showing you that data right now, but if you want, I'll show it soon. I'll show you it soon. When it's all properly aligned, it should look like this versus angle, and eventually it did. Okay, so this is after we achieved the proper alignment. Here's the Fabry Perot Etalon. Here is the laser going through, and you could see these nice, beautiful rings that are symmetric. A little bit it's cut off. This is actually my hand with a business card here, and this is with the lights off. You can see that the rings are nice and symmetric, and you get these nice symmetric rings when the Fabry Perot is exactly perpendicular to the beam path. When it's not exactly aligned, then those rings are like tilted to one side or the other. So we were eventually, thankfully, able to get proper alignment of the Fabry Perot relative to the laser path. Let me give you now this is actually in simulation, but let me give you a feel for what is actually happening when laser light goes through the Fabry Perot. So what do we have here? This dash we have as the x-axis wavelength, and we're assuming the wavelength of the laser is at exactly 532 nanometers. One second. Exactly 532 nanometers. That's this dashed line, and that's this spectral here. And this, by the way, what we have here on the y-axis is intensity. Okay, so this looks a little bit complicated. Let's go through it step by step. This is basically called the waterfall plot. This right here is spectrum as a function of wavelength for the angle being theta equals 0 degrees. And then I'm doing the same thing for theta be equal 0.2 degrees, 0.4, 0.6, 0.8, 1, and then 1.2 degrees. So these peaks here are the peaks, are basically the transfer function of the Fabry Perot Etalon. That means these are the wavelengths that get transmitted through the Fabry Perot Etalon. So for our exact Fabry Perot Etalon that we bought from Light-Machinary, based on the formulas. So at theta equals 0 degrees, you see that there's a transmission peak at this wavelength, and there's another one here, but there's actually no transmission peak at exactly 532, which means at exactly theta equals 0, we're going to see very little transmission of the laser through the Fabry Perot. As we vary the angle, the transmission peaks change their wavelength position. So initially we still see very little intensity go through because we're in this blocking region where the Fabry Perot is blocking the laser from going through. And then eventually when we get to theta equals 1 degree, then we have a lot of laser light going through because the laser matches up with one of these transmission peaks of the Fabry Perot Etalon. Now, if we look on the spectrometer, what do we see? If we look on the spectrometer, we see this. We see a peak at 532 nanometers, but with our spectrometer, we see a very broad spectrum, okay? If you look at this peak, this is you might, depends who you are, you might say, that's not so broad. That's like 1 nanometer. What are you talking about? 1 or 2 nanometers? Yeah, but 1 or 2 nanometers for the laser line is pretty broad. That's because our spectrometer has a resolution that's not so good. It's okay, but it's not so good. It has a resolution in wave numbers of 46 wave numbers. That's what our laser looks like without the Super-Spectral-Resolution technique. By the way, then we put in the Fabry Perot, and then we do this angular measurements, okay? And what we see then is if we look at the laser light scattered through, we see as a function of angle, again, at 0 degrees, there's no light going through because, like we saw in the previous slide, the Fabry Perot blocks the laser. But as we vary the angle, at some point, the laser light goes through. And then there's no light going through. And then at another angle, we get another resonant peak. So we get a series of peaks of laser intensity as a function of the angle of the Fabry Perot. And we can do that if we vary the angle in one direction, positive angle turning or negative angle turning. It's supposed to be symmetric. And then we use a fit of what the laser line width and laser position has to be to match this angular distribution. And what we found with the super-spectral-resolution fitting procedure is that the only way we could get these peaks to match up with the observed angular data is if we assume the laser was not exactly 532, but instead 531.962 nanometers. And we also had to fit it with a line width for the laser of 0.4 picometers, which is 0.014 wave numbers. Let me give you an idea of what that means. Okay, 0.014 wave numbers looks like a delta function on this graph. I can't even show it really. It would just look like a straight line. Okay, it's basically 3,000 times, more than 3,300 times narrower than what we measured. Now you might say, how do we know that this modeling is correct? So what we did is we varied the parameters in our model for what the line width of the laser could be. And we saw that indeed, only if this is the line width we use, could we accurately predict the angular spread. If we assume a larger line width, we cannot recover the angular distribution of the laser excitation. So we knew that if we can baseline the system, characterize the laser, and indeed we found the laser line is very narrow using our super-spectral-resolution technique. Then we said, let's go on to the diamond. So the story with the diamond is similar. We have the diamond peak. Diamond has a characteristic Raman peak at about 1,332 wave numbers. We varied the Fabry Perot, and we look at how the intensity of the diamond scattered peak changes as a function of angle, and we try to fit how that angular variation changes as a function of the line width and the peak position of the diamond Raman scatter line. And only if we have exactly the right parameters can we match that angular variation. And what we found is that when we apply the super-spectral resolution to the case of a natural diamond, this is what we get. The Raman peak without the super-spectral resolution is this blue line, which has a measured line width of about 44 wave numbers. It looks just as narrow as the laser because both of them look bad. Not bad, but both of them look relatively broad because that's the limit of what our spectrometer by itself gives. When we turn on the super-spectral resolution and model it, then we find we get a diamond peak that has a line width of only 1.63 wave numbers. So that's an increase of 27 times better resolution when we use the super-spectral resolution technique. So how can we summarize? We built a super-spectral resolution Raman, where we took a grating-based spectrometer and added the Fabry Perot, just like those good folks did in astronomy over 40 years ago. Only now we applied it for Raman and we did angular tuning. We applied the data, and sure enough, thankfully, we saw a very nice Raman peak. And what we want to do now is we want to try to actually see if we can distinguish between two different kinds of diamond, one that's lab-grown or one that's naturally grown, because maybe there'll be a very small Raman change in the Raman shift that up until now people didn't see because they just didn't have a spectrometer that had high enough resolution. So you can read about our paper, which we thankfully were able to just publish. It's so new, the date is even 2025. That's what the journal put on there. But we showed these results and the increase in the resolution. And let me just say, we're super excited about Raman going forward. We think there's always more to do and more exciting things to do. And hopefully now we can do those measurements with better spectral resolution. And I like to say there's a tsunami of data coming as Raman becomes more and more popular. There'll be more and more applications, And hopefully now it'll be even easier to do super spectral resolution for all kinds of applications, whether it's biomedical or in manufacturing, or even to detect, like in an airport, if there's explosives or heaven forbid, dangerous chemicals like drugs, or even for semiconductor metrology. Raman is a really powerful technique that many people know about. With that, I'd like to thank my lab, all the people there who are really the magic in making this work, and our sources of funding over the years, the Israel Science Foundation, the Israel National Nanotechnology Initiative, and even Erasmus Plus, who helped us out a few times along the way. And with that, I'd like to thank you and open it up for questions.
Thank you very much, Jacob, for this very nice presentation. Very nice. I think that you have very nice presenting to the students, even the fundamentals in order to understand your research results. So in this case, please stop sharing the screen to open the floor for the next 10 minutes because other things are coming for questions. I have some questions, but I would like to ask the audience, if you have any question, please raise your virtual hand in order to provide you the floor, or you can write your question in the chat. Before we start, I have a question, Jacob. And my first question comes, what is the linewidth? The linewidth, I prefer to give me this, this information of your laser source in kilohertz or in hertz, in frequency, not in the wave numbers. So what was the linewidth of the laser source that you have used? I suspect that you are using semiconductor laser under CW operation. Am I right?
Under what operation?
CW, continuous wave.
Yes, CW. Yes. Okay, to convert to wave numbers to linewidth, I can do that off the top of my head. I have to think about it for a second. It's 0.4 picometers. I have to get back to you on that one.
Okay.
But I'll get back to you soon.
All right. So my question here is I suspect that you are using a just semiconductor laser source. Semiconductor laser sources, of course, you need to stabilize the wavelength that you are using. Are you using any locking techniques in order to stabilize the wavelength of your source, or your source operates in room temperature, like
right.
a free laser?
We used hold on a second.
Bound-driven locking technique?
No, but this is a single mode laser from cobalt. So it's not locked to any standard, but it is considered single mode and single wavelength. That's all I can say. So it is supposed to be pretty narrow. I want to get you an answer to your question. I'll try to do that.
All right. So let me go on. The aim of my question is the following. There are other kind of techniques, other kind of laser sources based to semiconductors. I will give you external cavity diode lasers that they reduce a lot any semiconductor's laser linewidth. A lot. So you can go from megahertz to kilohertz, linewidth. And I'm talking about single longitudinal mode and single transverse mode laser diode sources. And if you couple them with an external cavity laser, external grating, in order to make this configuration of external cavity diode lasers, are extremely useful in spectroscopy. So I suspect that it's going to be extremely useful to provide even narrower super-spectral Raman results than the ones that you are running right now with a single semiconductor laser. More than this, if you try, this is not important, this is not possible because you are using a commercialized device. So the commercialized, any semiconductor, however it's a commercial, it has drifting because of the temperature drifting.
Right.
So you can, in semiconductor physics, in semiconductor laser, you can fine tune or you can coarse tune, your semiconductor by varying the temperature or even the current.
Right.
So, I will say that probably this is something that we can write, a proposal in the first case. If we can build, and we can build external cavity diode laser, the reduction of the linewidth of the initial laser source, for sure it will have better, higher intensity and excitation of the Stoke and anti-Stoke peaks with even narrower, let's say peaks, even linewidth, I'm talking about the spectral linewidth.
Yeah.
I mean, it is like at least 3 orders of magnitude if you compare the linewidth of a semiconductor compared to external cavity diode laser.
Wow. Let's talk about that more after. That's really exciting.
Okay, so
That could be really powerful.
This will check it. You can go and check. External cavity diode laser. You can buy them even. It was a German company that they used to sell it, and this was like because exactly my PhD. These kind of devices in order to use as a pump source in OPOs in order to do gas spectroscopy.
Wow.
But try this because this gives you more opportunity for even more, let's say, super resolution, let's say, vibrational spectroscopy. This is like my first comment. I would like also to ask you something. Is there any power threshold, let's say pump power threshold in order to excite this Raman, these Stokes and anti-Stokes peaks? So is there any minimum threshold regarding the pump laser source?
From what I know, theoretically, no. I mean, if you do it at a lower power, you will have a lower signal. But from what I know, the Raman, when it's a spontaneous Raman, it does not need a particular threshold. When you talk about a stimulated Raman, then there can be a threshold. But the stimulated process, you need a certain amount of excitation to see the stimulated process. But what I'm showing here is spontaneous Raman and super-spectral-resolution on spontaneous Raman.
So
if we wanted to talk about,
excuse me, if they are spontaneous, then if you will repeat this experiment with stimulated Raman, I suspect that the resolution is going to be even narrower, no? Because it's stimulated effect.
Yeah, so actually something I've been curious about, I have to admit, and I don't know the answer, but maybe you do. It sounds like you do. Sounds like you're on the right track here. I've been curious if we can try to combine our super-spectral-resolution approach with a stimulated Raman approach using either a high-intensity pulse laser or a frequency comb or all this kind of stuff, because sometimes those measurements require very complicated systems in the time domain, and maybe, hopefully, okay, maybe it's wishful thinking, if you can take the high intensity pulse laser and the Fabry Perot, maybe somehow you can get some spectral information out of it.
Definitely you should go, I think, to femtosecond, even narrower laser pulse in order to not induce extra thermal effects to your target material. So you need to go femtosecond and even attosecond laser pulses in order to do not degrade the material.
You guys have the attosecond in Crete. I know you have the whole center there.
No, I'm not. I can ask. I think Britakis is here. Probably Konstantinos. Probably he can ask, but definitely they have femtosecond laser source.
Okay, maybe we'll take this as an action item and then get back to you. I'm certain for discussion.
And my final question is the following. I mean, when do you induce these Stokes and anti-Stokes peaks? Because you excite, you make the laser matter interaction, and you observe. I mean, in the observation of these peaks, have you ever checked if you observe any polarization, light polarization of the peaks that you observe? Are there any linear polarized light?
Yeah,
of course, the semiconductors by itself is a linear polarized device.
So your intuition is 100% correct. Thank God. Actually, the Raman can be highly polarized, and the Raman is typically referred to as a Raman tensor, and measuring the polarization effects is a whole field in itself. For example, you can put in one polarization and then you induce that polarization, but then if the molecule has its own vibrational modes, it can rotate the polarization. And when you have a chiral molecule, you get different rotations. It's called Raman optical activity. It's a whole world in itself studying these effects. So the short answer is absolutely yes.
Thank you very much, Yakov. I don't have any other I don't have any other questions from my side. Very interesting things, and I think that very nice things can happen because, as you have mentioned, this is something exciting and new, and I mean, from the laser point of view, there are a lot of things can be done, and I'm very happy about this. George Kavoulakis, you would like to ask something? Thank you, George.
Yeah.
Hi,
First of all, many thanks for your talk. Very
You're
interesting
welcome.
stuff. I'm not on this field, but I have a very naive question. If I use photons or electrons, then my resolution is determined by the wavelength. Here that you have developed this technique, I understand. Is there any simple length scale that sets the resolution that I know from the beginning that I cannot exceed this resolution that with very simple arguments?
You mean what's the ultimate resolution limit?
Yes.
That's
I mean,
very simple question.
I think that this is determined by the reflectivity of the Etalon that he is using.
I was just going to say,
Distance of the Etalon.
yeah,
And he's using George. He's using a spectrometer by itself. Within the spectrometer, you have gratings. So the gratings induce some how can I say, some fine it makes the things with high resolution, and then you go also to Fabry-Perot, the distance of the Fabry-Perot and the reflectivity of the mirrors that the Fabry-Perot is constructing is also improving this resolution.
So I can talk to that point right now and say our Fabry-Perot, the short answer is there is a limit as far as I know, and I'll describe it now I'll try to describe it now. The Fabry-Perot specifications are that the peaks, the separation between the peaks is 2 wave numbers. That's the mode spacing. And the finesse is 30 is a factor of 30, which means that each peak is about 2 wave numbers divided by 30. So on the one hand, we found when we studied it, the resolution is limited to about 2 wave numbers divided by 30, so that's about 1/16 of a wave number. That's our resolution. However, there's a trick. Maybe we need to do this in our next study to emphasize this. And that is, the same way when it comes to imaging, there is such a thing called a point spread function, where you can have 2 peaks that are actually relatively close to one another, but if you can fit them, you can sometimes fit 2 Gaussians that are overlapped and get better resolution than a single Gaussian. So the same thing here is when we have one peak by itself, like the laser or the diamond peak, then we get a resolution that's even better than the 2 wave numbers divided by 30, because we're just fitting to one peak that's spectrally isolated. So the short answer is there is a limit to the resolution, but at the same time, if we can take many spectra, then we can somehow do better than the regular resolution limit of the Fabry-Perot by itself. We can do super resolution on the Fabry-Perot, is what I'm trying to say.
Okay, thanks a lot.
Sure.
However, the finesse and all the stuff depends very much on the reflectivity.
Absolutely.
And the distance between the mirrors that consist the Fabry-Perot. Is it a scanning Fabry-Perot, Yakov, or it's just like two standby?
No, that's the thing. Zev used the scanning one where he varied the spacing between the 2 mirrors. But what we did here is we bought a fixed one from Light-Machinary, and I sent you all the link to that website, and then we just varied the angle. Okay, we varied the angle. So we could have done it by changing the spacing, but we felt that varying the angle is a lot simpler and easier, and therefore maybe could be more applicative.
Thank you. Thank you very much. I think that we need to close because another meeting comes. Yakov, I would like to thank you very much. It was like a very clear and very nice presentation. I mean, at least I'm closer, and I could follow, the whole communication. It's an exciting field for our students as well. We have a very good collaboration with Jakob's laboratory, so it will be one of your options if you would like to do your final thesis. We can send you, through HMU to Jakob's laboratory in Tel Aviv. So thank you very much. We are going to renew our meeting next week. We're going to have a scientist from Portugal that is going to speak about wind turbines within the sea, offshore wind turbines, and how they can contribute to renewable energy sources and production of clean energy. So until then, stay safe and speak to you soon. Jakob,
Okay.
I'm waiting for your response about winters.
Okay.
Bye.
Bye for now.
Bye.
Thank you, everybody. Bye.
Bye.